Assalamu alaikum. Today we shall talk about reduction of organic compounds using another very important reducing agent, that is lithium aluminium hydride. So students, last time we were discussing the sodium borohydride, uh, its application as a reducing agent, and we learned its structure, that it has a tetrahedral structure and it is a hydride ion donor. It, it donates, it give off the hydride ion that actually reduces the other organic functionalities. Similarly, today we shall talk about the similar type of the reducing agent, that is lithium aluminium hydride. This is lithium aluminium hydride. It also releases hydride ion. Now let's compare the reactivity of these two reagents. We see that lithium aluminium hydride, it's a powerful reducing agent. It's powerful reducer. Sodium borohydride was moderate. It is a moderate reducing agent. It reduces only predominantly aldehydes. I should not write the name, I should write only the functional groups. Aldehydes, ketones, azides, ozonides, imide, and acid halide, etc. Few functionalities. But lithium aluminum hydride, it reduces almost every class of organic functionalities. It reduces aldehydes, ketones, esters, amides, acid halide, nitro, nitriles, imides, and oximes, substituted amides, etc., etc., and etc. You see that almost every important functional groups can easily be reduced using lithium aluminum hydride. Now, why it is a good reducing agent? Last time I have explained this. Now I'm going to add few more words about the reducing power of lithium aluminum hydride. The first different point of difference between these two is the counter ion. This is sodium, and here we have the lithium. Lithium has more charge density as compared to sodium. The second one is that this aluminium hydrogen bond is a relatively weak bond as compared to boron hydrogen. Why? Because the boron is relatively electron negative element. It it can accommodate this negative charge, so it binds this hydrogen more strongly, while this aluminium is a little bit electron positive. This is not as much stable structure as this borohydride ion was that. So it 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 definitely, in order to get some stability, it would have tendency to give off this hydride ion to to be formed in AlH3. So that's why this aluminum hydride is more powerful reducing agent as compared to sodium borohydride. So whenever someone asks you that why a lithium aluminum hydride is more have more reducing power, so you will see that because the aluminum AlAH bond is relatively weak bond, because aluminum is electropositive. It normally it don't have the ability to accommodate a negative charge. Electropositive elements don't like to have the negative charge on them, while the electronegative element, they like to have the negative charge on them. They can accommodate, although both of them have the empty pockets where they could accommodate the pi electrons or the pair of electrons, but since the aluminium is electropositive, so it normally it does not accommodate the pair of electron in its empty 2pz orbitals. So that's why it releases the hydride ion more easily, so it becomes the good reducing agent. Now what is the mechanism? So mechanism actually will depend upon which class of organic compound you are going to reduce. So let's talk about the first, ketones or aldehydes. So what happens, this aluminium this aluminium hydride, it hydridine as a nucleophile attacks on this carbonyl compounds, on this ketocarbon, which is polar bond. So when hydride ion as a nucleophile attacks on this electrophilic center, what will happen, that this pi electron density will move over the oxygen, and you will get negative charge on oxygen, and here you have the hydrogen. Now this hydride ion, because you know that the C double bond O, this bond where electrophilic carbon has sp2 hybridization, so hydride ion could attack from the front side of this planar keto group, or it could attack from the back side of this polar keto group. So I'm not going to show here the orientation of this hydrogen, so I am just writing like this. So you will have to assume that it could attack from both of sides, and oxygen is now gets negative charge. So when aluminium hydride, it releases the hydride ion, it becomes AlAH3, so its empty pocket becomes available, where this aluminium, this oxide ion donates this pair of electron to this aluminium. So what happens, you get this intermediate. AH3 negative charge on this. Here I will describe few things more which is quite different from the reduction that we studied last week. That alum reduction using lithium aluminium hydride, it occurs in highly non-polar solvent, highly non-polar solvents like tetrahydrofuran or diethyl ether, etc. There shouldn't be moisture or there shouldn't be water in these solvents. Why I'm saying this? Because this lithium aluminum hydride, it's a powerful reducing agent. It easily releases the hydride ion. So if there would be a water or if there would be any polar protic solvents, what will happen? The hydride ion will rapidly attack on this water and it will pull the hydrogen ion from them, whether in case of polar solvents or in case of water. So you will have AlAH3 hydrogen and O negative or hydroxide ion, and this hydrogen, it releases from the system and it may capture, it may ignite, so your whole reaction will burst into fire. So whenever lithium aluminum hydride is used in the reaction, your solvent must be non-polar and they shouldn't have any impurity of either water or the impurities of polar solvents in them. So that's why you will see that most of the reaction of the lithium aluminum hydride occurs in non-polar solvent. So what happened that ketones when react with the lithium aluminum hydride, it actually releases the hydride ion as a nucleophile, and this nucleophile attacks on the polar bonds such as C double bond O, C double bond N, C double bond S. So any polar bond, pi electron, pair of pi electron moves on the oxygen, so it becomes oxide ion. So now oxide ion donates this pair of electron to the empty pocket of the aluminium. So this is the intermediate that you get in the first step. In the next step, you perform the hydrolysis. So what happens when you perform the hydrolysis? So finally you get your reduced product. What is this? What is the name of this reduced product? It's alcohol. In case of aldehyde, you will have primary alcohol. In case of ketone, you will have secondary alcohol. So aldehydes or ketone get reduced on reaction with lithium aluminum hydride to alcohols. Here in this mechanism, another very important aspect needs to be noticed, that this hydrogen that I have shown in this not non-linear line, this hydrogen, it comes from lithium aluminum hydride, while this hydrogen, it comes from the water, acidified water that you add after the completion of reaction. So you will see during the workup of the reaction. So when, if I write this reaction, in the first step you are going to perform lithium aluminium hydride in tetrahydrofuran at low temperature. But in the final step you work up with D3O positive. Then what will be the product? So in the first step lithium aluminium hydride will react, so it will donate its hydride ion. Then pair of electron moves will move on the oxygen, and that oxygen will make a new bond with aluminium hydride, and followed by the hydrolysis. So I'm going to write here the product. Here you will see that these this difference between these two, although it's an alcohol, but you'll have to remember that this hydrogen came from lithium aluminum hydride, while this D deuterium atom uh, have come here from hydrolysis or during the workup. So this is the general mechanism in case of aldehydes or ketones. Now let's discuss the mechanism in case of amides, whether they are primary or secondary amides. What happens? This is amide. Amides upon reaction with lithium aluminium hydride followed by workup with hydrolysis, they change into amines. They change into amines. How this happens? This is important to practice and to memorize. Now I will just write a lithium aluminium hydride like this. In the first step, it reacts over here. Hydride has a nucleophile. It attacks on this carbon, and the pi electron moves on this oxygen. Oxygen gets negative charge, and that negative charge, the oxide ion, attacks on AlH3. So finally you get this intermediate, and this hydrogen that now came from lithium aluminium hydride. So what happens that the lone pair of the nitrogen, it reforms a new bond with this carbon, making carbon nitrogen double bond, kicking out this good living group. So you get this intermediate. What happens next? Again, another AlH3 hydride ion. This hydride ion, it attacks over here, and this bond moves back. So you get minus AlAH3. So what you are getting? You are getting the amines. Here I would like to add few more words regarding the reactivity of the lithium aluminium hydrides. Lithium aluminum hydride does not reduce non-polar isolated bonds such as carbon carbon double bond. Isolated, it should be isolated. You have to pay attention upon my words, that what I am saying, that this carbon carbon double bond should be isolated. It's a non-polar bond. Similarly, carbon carbon triple bond. Let's see few examples. Now this is a starting compound. No, you don't need to remember the name. What is the name of this compound? Just draw their structure on the chem sketch or chem draw, and upon when you will click on the nomenclature, you will get the complete name of this compound. This is a very beautiful example where the stereochemistry of this reaction will also be described. The hydrogen is on the front side while the methyl is on the back side. Now, what are the functionalities that are going to be reduced? Here we have olefinic double bond, and here we have a keto group. And I have just explained you that the lithium aluminum hydride does not reduces the isolated double bond or triple bond. So this is very much isolated. It's not a part of any conjugation. It's not a part of another ring or benzene ring. So this single double bond is isolated. So what happens now? You see that you will have to focus on this functionalities, keto group, and lithium aluminum hydride. It will release the hydride ion, which will act as a nucleophile. Now, I have already told you that this planar keto group, it has two phases. So hydride ion could attack from the front side, this as compared opposite to this methyl, or it could attack from the back side, from the same side where this methyl group is pointing. So what do you think that approach of this hydride ion or this bigger lithium aluminum hydride will be more feasible? Whether the hydride ion will attack from the front side or it will attack from the back side. So when lithium aluminium hydride it approaches the keto group from the back side, there would be the steric hindrance during the approach between this methyl group and the bigger lithium aluminium hydride. So when it will approach from the front side, what you will get, hydrogen will be here and O will go on the back side. And finally you will perform the hydrolysis, so your final product will be this one. Hydrogen. Let's talk another beautiful example of stereochemistry in the reaction. What is the name of this compound? So you will see that one, two, three, four tertiary butyl cyclohexanone, and this is equatorially oriented. Equatorial. Now, what will be the product? Whether the product will be this one or product will be this one. Now we are going to learn the stereo selectivity of this reaction. Now let's discuss by writing the mechanism of this reaction. Since this polar carbon double bond oxygen polar bond, it has two phases, and lithium aluminium hydride, it will release hydrogen as a nucleophile. Now when this bigger lithium aluminium hydride, it could approach from this side, from the lower phase opposite to this tertiary butyl group, or it approaches from the upper phase of this carbon double bond oxygen. What do you think, that which approach will be more easier? As it is clear that when it approaches from the upper phase, then there will be the steric hindrance between the tertiary butyl group. This tertiary butyl group is quite large. I'm not showing the methyl groups. So when this approaches from the upper phase of this carcio double bond, then there would be steric hindrance between these aluminates or aluminum hydride and this tertiary butyl group. So it will approach from the lower phase of this C double bond. So what you will get this transition, this intermediate. and upon hydrolysis, final workup, you are going to have this compound as a major product. So you could also write it like this, that OH and these tertiary butyl group, they are cis to each other on the same side. It is on pointing upward and OH is also pointing upward. Now I am giving you a problem to solve, and you will have to tell me the answer on WhatsApp. So students, this lecture is quite big. I'm going to split this whole lecture of the use of the applications of lithium aluminium hydride as a reducing agent. So I have just explained you the reduction of reduction of the ketone and aldehyde and amides using this lithium aluminum hydride, and also I have described the stereoselective aspects of the reactions. So later we will continue this lecture. Now this is your starting compound. Upon reaction with lithium aluminium hydride in THF followed by workup with acidified water, what will be the product? You will have to tell me. So thank you so much.